The next talk will be given by Andy Thomas, also from the Leibniz Institute in Dresden, and he will talk about in-situ magnetotransport applications of manganese, platinum, tin. So go ahead, Andy.
So yeah, thank you for inviting me to give this talk of this very nice workshop. And I would like to show you our investigations of manganese, platinum, tin. And of course, first I would like to thank my collaborators, mainly the students who did the work. Here's some with pictures and some without pictures. But as you can imagine, if you do transport experiments in a transmission electron microscopy, you need some experts in the respective fields. So you see on the left-hand side, Darius Pohl, who is an expert in transmission electron microscopy and in more particular Lorentz transmission electron microscopy. I'm more of a magnetism transport person. So the two of us collaborated on this project to do look at the transport and the TEM at the same time. And there's more people involved. Most prominently, it's Dominik Kriegner from the FCU in Prague. It's Claudia Felser, who made the single crystals in her group in the Max Planck Institute. And then there's Bernd Rellinghaus, who's the head of the Dresden Center for Nanoanalytics, where the TEM group is located. And of course, last but not least, there's the funding agencies on the bottom there you can see. And without them, research is, of course, not possible. Let me start with a very short motivation on how we prepare the samples and how we came up with the idea to do these in situ investigations in a Lorentz TEM. In this case, it's a material a little bit longer ago. It is cobalt, tin, sulfur micro ribbons, and on the lower left, the top left here, you see the single crystal, and you can see this hexagonal shape of this single crystal very nicely. It's embedded in the back in some glue because of the TEM guys. And there you can see here now on the top and on the side, you can cut by focused ion beam what normally becomes a TEM lamella, but you can also place it on a substrate. In this case, we normally place it on MgO because it's completely not conducting. And you can put the contacts here. So here you see the strip, the hall bar, side contacts, you can feed the current through. Then you have on the left and on the right side two thermometers, two 4-point thermometers. And on the very left and on the very right, there's a heater. So in principle, we can measure Seebeck Nernst, longitudinal and transversal resistivity. Normally, we are interested in the Hall at the same time. We put them on a chip carrier and then we measure them. However, in the Lorentz TEM, there are some developments. The Lorentz TEM has very nice resolution. So, and there's these fermions. And these fermions, you see one of the images on the left-hand side, they should yield topological Hall effect. And on the other hand, there's some materials that transport people like me investigated, and they indeed found some topological Hall effect. So the idea is how, if we place a ribbon of a material that shows skyrmions, anti-skyrmions, something like that, on one of these TEM substrates, we utilize this holder, we have electrical feed-throughs at the same time, and then we can measure the electrical resistance, the transversal and longitudinal resistance, while subsequently measuring Lorentz TEM. So for every data point, we can have a transport data point. So maybe it becomes a little bit clearer if I give you one more concrete example on a simple material. In this case, we chose nickel as a material of choice. So you see on the top-hand side is again the sample holder, and on the right there is the SEM image of the actual Hall bar structure with the single crystal here in the center. And these are the CAD drawings of the Lorentz TEM holder, and on the lower right side, you see a false color image of the actual Hall bar. So if you go now to the right side from the design to the actual lithographic image of the nickel, you can see the contacts in a more blackish color, and the grayish color here is the nickel strip. We wanted to have a simple material just to see if everything works. So we have basically 4 contacts, two longitudinal ones where we can feed the current through, and 2 transversal ones where we can measure the voltage, while at the same time, of course, we can measure the longitudinal voltage in 2-point geometry as well. And because there's this window in the very center, you can see it here a little bit nicer, where we put our strip, we can do Lorentz TM images. So this is here now again for the nickel. On the left top is the cartoonish image again on the structure. So you feed the current in one direction and you measure the voltage in the other. You have a perpendicular magnetic field and you get 2 data sets, one Lorentz TM image in one hall for the same area where I put the black frame around it, and the darkish color is basically where you look with the TEM, and at the same time, because it's the hall bar cross, this is where you will receive your information from. And there's 2 images now where you can see the domain structure of the nickel, and I don't want to go into the detail. That was our test measurements basically to confirm that we have a material where we know what's supposed to come out, we can explain, and we can measure. Okay, so now let's go to the interesting material we are really looking into. And like I said, we wanted to look at the topological Hall effect, and we need some material that shows topological Hall effect and has skyrmions or anti-skyrmions, something like that. And this is material that shows anti-skyrmions, and most prominently they show it at room temperature. It has to be room temperature because the TEM holder we utilize in the TEM cannot be operated at lower temperatures. You can either, at least in the setup we have, you can either go to low temperatures and do Lorentz TEM, or you can go transport at the same time, but then you're stuck with room temperature. So of course we are interested in a material that shows anti-skyrmions or skyrmions at room temperature, and manganese 1.4 platinum tin did us the favor. It was a very nice pre-characterized material by Professor Felser's group from the Max Planck Institute, and this is what we chose for this investigation. This is now a false color image SEM overlay of the actual ribbon. You can see here in yellow color is again the feed for the current that goes through the sample here, and here you see in greenish color the Hall contacts. And what was done, it's not very visible here because it has very low contrast. The TEM guys went ahead and removed the silicon nitride membrane from parts of the back of the substrate so we can have even higher contrast. So we only put the electron beam through the material and not through the silicon nitride as well. Okay, so if we do this now, this is again the cartoon, which did not change. So the idea of the measurement is the same as before. And as you can see here, this is the Hall signal, and it looks the same if you look at other publications from the same material as expected. And the interesting thing is now for every data point that you can see here that was collected for the transport image, if I look now and start the video here, you have a Lorentz TM image. And it's very hard to catch, but in this intermediate region, you will see the anti-skyrmions appear, and between that, you have the chiral soliton lattice structure. Let me just play it again. It looks kind of cool, unless, unfortunately, this is not so nice to analyze the data. So I will do that with some still frames in the next slide. But before that, we have to think, is the model that we think we have to explain these images really correct? And to test the consistency of the image, we generated a OOMP file and fed it basically into this nice Lorentz TEM simulator with all the parameters of the TEM that we have. So we have this very simple structure at 0 magnetic field. We come up with a simulation, and as you can see here, the surrounding image is the actual Lorentz TM image, and is the Fourier filtered Lorentz TM image, and it nicely corresponds here to the top image of the simulation. It's a little bit harder to see because the contrast is not so good, especially if you are looking on a projector. So here I chose a line scan. Basically, we cut through the lines perpendicularly, and then we see, we look at the experiment and at the simulation. And as you can see, again, in this case, at 210 millitesla, it is a very nice resemblance of the Lorentz TM image and of the structure that we actually expect from our simulation. However, as it turns out now, you can do different simulations. I don't want to go into the detail because we will not use them in the end at all, but you can look at the blue dots, which is the very simple, most straightforward view, and then a little bit better one, greenish. But if you look at the error bars, and that's my main point, you see they get quite large. And I put the arrow here where we have the region where we are actually interested in. So this is where the images reveal the antiskyrmions, and you see this little pocket here of the Hall effect. So we want to somehow relate this pocket to the possible occurrence of a topological Hall effect. Yeah, it's not the big one, this one here, which is just a simple hysteresis, depending on when you get the chiral soliton lattice, but it's this little pocket here that we want to try to explain. And for later reference, so the overall amplitude of the anomalous Hall resistivity is 2.6 microohm centimeter. So here again, same thing in a different view graph. So we have the chiral soliton lattice here at 16 millitesla. Here we have the antiskyrmions in this red dot region, a red circled region. And this might or might not be the topological Hall effect. And it is 3% of the anomalous Hall signal. However, the sweep does not have enough resolution to actually reveal that. So what did we do? Instead of making a Hall sweep, which is of course to most of you the most common way of doing it, we now tilt the sample. So basically, instead of this Hall sweep that I've shown you, so you have all these images and you have the region with the antiskyrmions. I have now a video, and how you can imagine that is you have this window in the Lorentz TEM, and you can tilt the sample like this, and you can tilt the sample like this. And it had been published before that if you tilt the sample, you can actually change the system to do preferably magnetic non-topological bubbles or antiskyrmions. So we are in here at a certain field that is very close to the field where you see the antiskyrmions also in the normal field sweep. And then we tilt the sample. And while tilting the sample, we look at the Lorentz TEM image. And again, at the same time, we look at the transport data. So let's do that again here first at the video. So let me show you the video. You see all these bending lines and other artifacts that unfortunately you have in Lorentz TM image. But if you look carefully, so first you have something really like a lattice almost. So if you try to focus your eye on one of these things, they seem to stay pretty much in position. But you will see there's this bullet kind of shape, which is a non-topological bubble. And there is a more squarish shape with some structure inside, which hints to a antiskyrmion. You see here we start with these squarish things that are antiskyrmions, and then we go to these more bullet or circle shape that are non-topological bubbles. And again, this is very nice to look at, but to analyze the data, or at least in a talk, it's nicer to look at some representative still images, and I want to do that here. So here again in the center, you see what we did. We have the sample, and we can now tilt the sample in a magnetic field that is very close to the perfect moment where in the field sweep the antiskyrmions appear. And you see here now, depending on the angle, so let's start at 12 o'clock, basically on the top. So you see this squarish shape, and I put some kind of legend here on the lower right? So we have the antiskyrmions, and here you see the contrast changes. So here we have bubbles, 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 and then at -7 degrees we recover, we get the antiskyrmions. At -8 we still have the antiskyrmions, and then if we tilt more and more, the antiskyrmions go away. And of course, when you tilt, come back, they reappear basically pretty much at the same position. We are a little bit limited just physically, so to say. You cannot tilt 90 degrees or something, and you would not have a TEM image, obviously, but our tilting range is limited to, I believe, ±21 degrees. And that's basically what you see here. So again, now this is much nicer to actually correlate the data that we collected from the Lorentz TM imaging at the one hand side and from the transport data on the other side, and just try to reference them and see whether we can observe the topological Hall effect. Again, the expectance of at least me, and I guess of most people that that would think about this experiment, is you have these this lattice of, or this regular pattern, let's not call it a lattice, of these entities, and they are all either antiskyrmions or they are bubbles. When they are bubbles and you tilt a little bit more and they become antiskyrmions, we have this additional contribution of the topological Hall effect that could either be positive or negative, and we expect some kind of a jump in the Hall signal when they become antiskyrmion, and then a jump back when they become a bubble again. Just remind you, it's not the same as having a uniform magnetized structure. And we did some micromagnetic simulations, and the bubbles and the antiskyrmions do us the favor that the overall relative magnetization remains the same. Because now we mix, of course, in our experiment, the observation of the anomalous Hall effect, which is basically how far we are from saturation magnetization, plus the topological Hall effect. But the bubble and the antiskyrmion have the same anomalous Hall effect because they have the same relative saturation magnetization. Okay, but anyway, so somebody was sitting at the computer of the DCN and was basically tagging these entities by either being a bubble or an antiskyrmion. And you see this is quite simple, right? So you have here this antiskyrmion is this squarish structure, and you have this other more organic shape, which is a bubble. And if you do that, you end up with a top right view on this picture. So this is now the ratio between antiskyrmions and non-topological bubbles. And you see it goes up to 4, which means at the extreme case, at one particular angle where we have the most antiskyrmions, we have 4 times as many antiskyrmions as non-topological bubbles. So it's like 80-20. And on the way back, we don't quite reach that. We have 2, but nevertheless, we have these distinct angles of, let's say, -3.5 and -7 or 8 degrees, where we have the most antiskyrmions. And most importantly, you see here on the saturation side, or not saturation, on the extreme tilting side, we have only non-topological bubbles. If we have now the relative normalized Hall signal and we tilt it, of course, the projection is a cosine of the tilt angle. So what we expect is this cosine or inverse cosine shape on the way back and on the way forth. And this is the fitted red and the fitted black line. So what we do now is we subtract this trivial geometric contribution to the signal, and we end up with what we call relative residual, which is the difference between the expected change of the Hall effect due to the tilt. And as you can see, this is within our experimental resolution, I would say pretty much a straight line. And so is the black one, which is the 2 tilting directions. So I hope you would agree with me that as opposed to what you might trivially expect is here where we have the antiskyrmions and here where we have the antiskyrmions, we have no additional signal. So we have an anomalous Hall resistivity of 2.6 microohm centimeters, I've shown you before. And the topological Hall resistivity that we can extract here is basically smaller than 2.4. You can never prove that there's something not there, but if it's there, it's well below our experimental resolution. And with that, I come to the conclusion. So our topological Hall effect can be well explained. Our Hall effect signal can be well explained without the additional contribution of a topological Hall effect. And yeah, we simply can explain everything we observed with the anomalous Hall effect being proportional to the saturation or to the relative saturation magnetization. And with that, I'm at the end of my talk, and I thank you for your attention.
Are there any questions from the audience here? Yes. No,
yeah, maybe the question about the data analysis. So the data looks like they asking for analysis in kind of correlation, Fourier transformation, or even better, super resolution with machine learning. Are you doing, or do you plan to apply this kind of analysis?
So we analyzed first by having a person basically tagging the antiskyrmions and the bubbles, which is very boring. And of course, this is now our first task was to try, or not my task, but of the DCN guys. And they are doing now this via machine learning. So they told this is how a bubble looks like, and this is how an antiskyrmion looks like, and it yields the same results. But of course, it's not as boring and it's much, much faster to do that.
It looks like perfect the task for such machine learning.
Yes, yes.
Can I ask a question here? Very simple question concerning the pictures that you now have on the view graph here. If you look at the square things compared to these bubbles, what is the skyrmion charge of the square bubbles, of these square objects?
So if I'm not mistaken, it's -1 because it's an anti-skyrmion.
How do you actually get that number?
Well, I mean, there is other people who investigated this material in detail, and there's some calculations regarding that. And if we compare our data with the pre-existing data and calculations, basically it just matches that. So I have no reason to question those.
Anything else? Are there any questions online?
No, I don't see.
If not, then let's thank Andy once again for a great talk.